more or less. We're going to do a ton of examples on this, by the way. So if you feel like I didn't quite get my fill of fatigue failure problem examples, you know, talk to me again in 3 weeks. We'll do plenty of examples on this. Because essentially the next part, where we're going to talk about shafts, part A, we're not introducing any new theory. We're just saying we're going to now talk about design of shafts because it's the most common machine element. But essentially what it is, it's a fatigue failure problem where we have some static loads in addition to it, right? So this is going to be exactly what we're doing right now. So we got 5 minutes left. What I want to start on, did we at least address most of the questions that were here? Do you feel comfortable moving forward? That doesn't sound... Okay.
Would it be possible for you to just put a sheet together and post on Canvas that defines these variables that you're using, E prime, sigma A?
Yeah, the problem is that we have multiple A's.
Okay.
So you have to derive it from the context, kind of. But what I'll do is, and this is typically what I do the first lecture when we talk about shaft, is I'm going to go with you through an entire recipe of how to do a shaft calculation, okay? And what we just did is a shaft calculation where there are no static loads. So we'll come to the more, we're building out to the more general case of shaft calculations. I'll give you an entire recipe, and if you follow that recipe step by step, you know, you are going to go through the entire calculation. You're not going to make any mistakes. You're going to learn how to calculate. Okay? So, but we're building up a shaft. All right, 3 minutes. I still want to introduce the problem or the thing here because I also would like to assign the homework today. You won't be able to solve it completely, at least in part. I need to assign it today though because we need to have a homework on fatigue and shafts before the midterm, second midterm, and that's the Friday after spring break, right? So I want to front load the homework because typically you guys are going to work hard on your mechatronics robot after spring break, and so after spring break we only have 2 more homework sets for this course, and so then your attention is to shift perhaps a little bit to electronics. What does that mean? We're already working on your road, is that what that means? Or? Okay. Alright, let's just quickly introduce the topic of fluctuating stresses. And remember, a fluctuating stress, if you look at it as a function of time, and this was the amplitude, is an alternating stress that has been shifted upward or downward. And so let's quickly define the nomenclature here. So this here, we're going to refer to as sigma m, the mean or steady stress component. That's the amount by which the alternating component has been shifted up or down. If it's positive, it's shifted up. If it's negative, it's shifted down. It's compressed, right? This here, we already know that's sigma A. That's our stress amplitude, okay? And then, of course, this would be sigma min. Pretty obvious. And then this is sigma max. And the important question now is, how do we define fatigue failure for fluctuating stresses? You can intuitively appreciate that because here we define the safety factor and we compared our alternating stress component to the endurance limit. But that's only the alternating component. What if we have a steady component in addition to it, right? It's probably not fair to compare that steady component to an endurance limit because one is alternating and one is steady. So that's not going to work well. So we're going to have to come up with fatigue failure criteria. And let's first look at the 2 limit limiting cases. The first limiting case is an alternating stress, where we set sigma m is equal to 0. Right? So sigma A is different from 0, sigma m is equal to 0. That's the limiting case of a fluctuating stress, so sigma m is equal to 0. So when do we get failure in that case? Well, if sigma A is larger than sigma E, that will create failure. Or sigma A larger than sigma F if it's not for infinite fatigue life, right? So it's for finite fatigue life. The second limiting case is a steady stress. If you have a steady stress, then sigma A is equal to 0, and sigma M is different from 0. When do we get failure in that case? Well, when sigma M is larger than sigma yield, or sigma M is larger than sigma UT. So you see that the real case, or the real failure criteria, must be somewhere in between these two cases, right? The two limiting cases where one is pure alternating stress and the other one is a pure static stress. And so there are three failure criteria that we're going to deal with. They're very similar to each other. The first one is the Soderberg failure criterion. The second one is the Goodman failure criterion. And the final one, the third one, is the Gerber parabola, which we're going to deal with. And we'll talk about that on Friday. Like